So I am asked to advertise this what promises to be a wonderful conference and event. So Singularities in the Plovdiv. So it will take place this year in June, and there will be 2 events. So one satellite event in Sofia, and the other the week after in Plovdiv. Okay, so I will talk about motivic invariant birational maps, and I will first explain what they are. And to do this, I will first talk about some questions in Kolmogorov group as a pretext. So for my talk, K will be a field. So for the moment, arbitrary field, but the statement question we will be talking about is sensitive of the base field. So later it will change it, but I will be more precise later. So far, it's just an arbitrary field. So let me write some questions about Kolmogorov groups. So the first question is whether Kolmogorov groups are simple. So Kolmogorov group by definition is the birational automorphism group of a projective space. So defined over the base field K. Is this group simple? Simple as a group. Answer we know in general is no. And this was first proven by Contalami in 2010. No when a dimension is 2. And Contalami proved the non-simplicity when K is algebraically closed, and then later Lonjou generate the non-simplicity for arbitrary field, but still for P2. And we also know that the Kolmogorov group is not simple when in higher dimension. And more precisely, for all field, which is a subfield of C, this is due to Brun-Lamy-Zimmermann. And more precisely, they show that there is this, we can always find a surjective group homomorphism from the 3-dimensional Kolmogorov group onto direct sum of Z mod 2, and then the number of factors has the same cardinality as the base field. Okay, so this is due to Brun-Lamy-Zimmermann. Also quite recently, 2019. Okay, so let me, so this is first question. Another question about Kolmogorov group is about what are the possible generators of a Kolmogorov group. This, for instance, we have this question first asked at least maybe by many people, but at least Logarithmic has asked this question. So the question is whether a Kolmogorov group is generated by a finite order elements. So it's BRPN generated by PGL, so namely the automorphism group of Pn and finite order elements. There is also, maybe let me write here. There is a related question asked by Vanya Chesov, replacing finite order element by regularizable elements. Okay, so let me write it as question 2 prime by Vanya Chesov. The same whether Pn k is generated by just by a regularizable map. So regularizable means that say that a birational map from Pn to Pn is regularizable, means that there exists so first of all, another birational map phi from the projective space, but to another variety, such that there exists automorphism of x, making this diagram commutative. So this is the definition for f to be regularizable. And here, there are, in the literature, there are some slight difference about the definition of regularizable. And here, in this talk, my definition is quite flexible. So I don't assume, for instance, x to be projective. So x can be just, for instance, an open in Pn. So for instance, automorphisms of the affine space, according to her, this definition will also be her regularizable element. X, you mean G?
Yes, X is any variety.
Any variety, yeah. And phi is any birational map. Okay, and let me write some positive answer. So the answer is yes, and again, the question depends on the base field k and also the dimension n. And yes, for n equals 2, for the following base field. So first of all, if the base field is algebraically closed, so this is classical due to Noether and Castelnuovo. Already more than 100 years ago. And more precisely, we know that for P2 over an algebraically closed field, the whole birational automorphism group is generated by the automorphism of P2 together with the standard quadratic transformation, namely the map sigma, where sigma is sending to write in terms of homogeneous coordinates, then it sends xyz to its inverse. Okay, so clearly this is finite order, so it's an involution. And recently, we also know that the answer is yes also for P2, but over arbitrary perfect field. This was due to Lamy and Schneider. Okay, and later we'll see. Later, I will introduce motivic invariants of birational maps, and then use this to provide some answer to both question 1 and question 2. Okay, so let me start by defining what invariant we consider. Okay, so here, actually, motivic is in the most elementary sense, so in the sense of a Grothendieck ring of varieties, so this is a baby version of motifs. Okay, so the setting is the following. So let's consider x and y, both irreducible varieties over K, and then we let F be a birational map from X to Y. And so birational map is well defined as a morphism at most points, but at some points it ceases to be well defined. And then for any birational map, we can consider the sets of exceptional divisors at both sides. So one way to define exceptional divisors of a birational map F is to say that they are codimensional one points in X around which F is not an isomorphism. So namely, F is not an isomorphism at X. Okay, so this is my notation for codimensional one points. So as and here we view X as a scheme. Namely, they are the generic points of irreducible codimensional one subvarieties in X. Okay, so the set of exceptional divisors denoted by X F. Okay, now the definition. So the motivic invariant that in the title is the following. So something denoted by a C of F, and which is just the formal sum of all the exceptional divisors of X inverse minus the sum of all the exceptional divisors of F. And this, we view them as an element inside the free abelian group generated by varieties, but modulo birational equivalence. Okay, so this will be my notation of this group. So this group is similar to what so John talked about, this free abelian group generated by her stable birational types. And here we just replace a stable birational by a birational. Okay, so so as I said, BK is for me the set of irreducible varieties over K modulo birational equivalence. Okay, so before moving on, let's see some first examples. So for instance, if we have a closed embeddings of smooth varieties, so both Z and X are, say, irreducible and smooth. And then if we consider a blow up of X along Z, And then the invariant associated to this blow up is then equals to minus z times PC minus 1, where C is the codimension of Z. Okay, so yeah, because the exceptional divisor or the preimage of Z is the only exceptional divisor of this blow-up map, and the inverse doesn't have any exceptional divisor. And we also know that exceptional divisor is a P, is a projective bundle in projective space, and which is birational to just Z cross PC minus 1. So this is the first example. And so in our setting, X and Y are really just arbitrary irreducible varieties. So for instance, we can also consider open embeddings. So these are also examples of birational maps. And for open embedding, if so the invariant associated to it will be the sum of irreducible components of boundary divisors. So here, these Di are irreducible divisorial components of the complementary of U in X. And then, yeah, third example is that, so by definition, if neither F nor F inverse contract divisors, then the invariant is 0. So namely, if a birational map is an isomorphism in codimension 1, then the invariant you get is 0. Yes, yes. Yeah. So I identify the residue field with the birational types. Yeah. Sorry. So yeah, this notation K of X is the residue field of the variety at the point X. Okay. So the key property of this invariant is that it is additive. Namely, if you take the composition of two birational map, and the invariant of this composition is the sum of this, the invariant of each map in the composition. So this gives some group homomorphism from the birational automorphism group of a variety to some abelian group. This property is, the proof is very elementary, and let me do now. In order to prove this, so let's take, first of all, let's consider a birational map, and then consider the factorizations by open embeddings. Okay, and if D is the dimension of the varieties X and Y, so let me first consider this element, so x minus u, y minus u minus x minus u in the Grothendieck ring of variety, but truncated by a dimension up to d minus 1. Okay, so the definition of the truncated Grothendieck group is similar to the definition of a Grothendieck group of varieties, but the only difference is that the generators we consider we only consider varieties whose the dimension is at most d minus 1. And then we mod out by the cut and paste relation, namely whenever you have a variety d, then if you take some say open or closed sub-variety in w in d, then we'll have d equals d minus w plus w. Okay, so this is this is the Grothendieck group of variety that we consider. Later, I will comment on why we need to take truncated Grothendieck group instead of the usual one. So this element I will denote by c tilde f. So it will be y minus u minus x minus u in k0 var smaller than or equal to d minus 1 and over k. So the first thing is to verify is that this c tilde is well defined, namely independent of the choice of the factorization by open embeddings we choose. But then this is very straightforward because so C is well defined. Because if you, it suffices to show that if you take a smaller open in U and then consider this factorization, then they define the same C tilde. So for any open V in U, then we just notice that by cut and paste, x minus V minus x minus U, this is U minus V. But then the same thing, you can do it also for y. And then if you move the terms around, you get that C tilde of f defined by U is equal to C tilde of f defined by V. Okay, and then once C tilde of V of f is well defined, then the additivity of C tilde is also straightforward. Because if you take so composition of birational maps f and g, Then we can take a common factorization of this map by open embeddings. Then by definition, C tilde of G composed with F. Now this is just Z minus U minus X minus U. And then we can plus minus Y minus U. So what you get is C tilde of F plus C tilde of G. And finally, it's sufficient to notice that the original invariant C factorizes through C tilde. Through the homomorphism from K0 of a truncated Grothendieck group of varieties to the free abelian group generated by varieties of dimension d minus 1 modulo a birational equivalence. This map denoted by pi. And the definition is that, okay, suffices to define on the generators of K0, and K0 can be generated by irreducible varieties. If I take one, call it D, then the image of D will be either just the birational equivalence class containing D, if dimension of D is exactly equals to D minus 1. And then it is sent to 0 otherwise. Okay, and again, we check in a quite straightforward way that this assignment is compatible with the cut and paste relation, which defines us group homomorphism. Okay, and by construction, the C in the key property over there is equal to the composition of C tilde with this morphism pi. So this proves the additivity of the invariant. So let me draw a remark. If we consider a birational automorphism group of some variety X, then look at the invariant C tilde that we defined in the proof. So which is a lifting of the motivic invariant introduced that we introduced first. And then the let me write this again on blackboard by drawing this commutative diagram. So what happens if we consider just the ordinary Grothendieck group of varieties, namely look at the further compose with this natural map to the Grothendieck group of variety, then by construction we see that then the composition is always 0. Well, there is no there is no lifting of this motivic invariant C to the ordinary Grothendieck group of variety, but only on the truncated one. Okay, so by the additivity of the motivic invariant, one corollary we get is that if you take a regularizable map, then the motivic invariant of this map is always 0. So if F is regularizable, then C of F is 0. Yeah, because then C of F is equal to C of phi plus C of G plus C of phi inverse. And then again, by additivity, we know that C of phi inverse is minus C of phi. And then since G is an automorphism, C of G is also equal to 0. And therefore, if, going back to our questions about a criminal group, look at the group of birational automorphism of a projective space. If the motivic invariant is non-zero for some element in the criminal group, then we know that the subgroup generated by regularizable elements, and even the normal subgroup generated by them, will be a strict normal subgroup of the criminal group. This is also because criminal group is, if n is strictly positive, then criminal group is non-abelian. But the target of the motivic invariant is in the abelian group. So if this morphism has non-zero image, then necessarily kernel is non-trivial. And then by the first statement of the corollary, this kernel contains all the regularizable elements. And then, and then finally, we have non-vanishing indeed for some n and k. So the image of the motivic invariant of criminal groups is non-zero in the following cases. First of all, when dimension is equal to 3, and when the base field is small enough in the sense that, for instance, either number field or function field over an algebraically closed field, then some birational automorphism of a P3 has non-zero. We can show that they have non-zero motivic invariant. And these maps for which the invariant is non-zero already appeared in a paper by Mori and Mukai. When they study classifications of Fano threefold. Yeah, so let me continue here. Yes.
Can you say what they are?
Yes, if I have time. So yeah, maybe after, at the end of the. And it's non-zero also for four-dimensional projective space, assuming the base field has characteristic 0. And for this, we can verify that some birational automorphism defined by Hassett and Lai have non-vanishing motivic invariant. And finally, when n is, so when the dimension is larger than or equal to 5, and for k any infinite field, so we can also exhibit some birational automorphism for which the invariant is non-zero. For instance, in dimension 5, there's already some birational maps constructed by Ito, Miura, Okawa, Ueda, that for which we can show that this invariant is indeed non-zero. So as a corollary, for all these dimension n and the base field k, as in the non-vanishing theorem, we obtain negative answers to all the questions at the beginning about columnar groups. Yeah, so Cesius asks about threefold. Maybe let me describe the example of Mori and Mukai now. Very good question. We think that no. So yeah. So typically, yeah, preimage of Z mod 2 will be some Sakisov links. And more precisely, some what we call type 2 Sakisov links. And they should have a 0 motivic invariant. Yeah, by the way, so all this work about which study this question on columnar group are all based on quite different technique and input. For instance, for Konta and Lamy, they obtained the non-simplicity by studying the action of the columnar group on some infinite dimensional hyperbolic space. So which is the Picard-Manning space, but endowed with intersection pairing. And then Bro-Nami Zimmermann obtained this through Sakisov program in the minimal model program of birational geometry. Okay, so Yeah, example for n equals 3 and for k, the base field as in the above. So let's take C, which is a smooth projective genus 1 curve without rational point, but with degree 5 effective divisor. And therefore, by Riemann-Roch, this divisor gives you an embedding into a P4. So it's a normal quintate curve of genus 1. And we know that scheme-theoretically, this is cut off by the linear system of quadrics passing through it. So therefore, in this system of quadrics passing through C defines birational maps from P4 to another P4, namely the P4 of this system of quadrics. Now we take a quadric containing C. Then the image under this birational transformation will be a P3. Let's call it phi. So phi has the following factorization. So we first blow up C, and then there's a divisor that we can contract, and we contract it, and the composition is this phi. So now what is the image of the exceptional divisor of the other contraction? And it turns out that it is, let me write it this way. So yeah, it turns out that the blowdown center is a second degree Jacobian of C in P3 because the exceptional divisor in Q, exceptional divisor of this P4 to P4 contracts the secant variety of C. So that's why the blowdown center of this transformation is Jacobian, second Jacobian of C. And then since this curve has no k-rational point, this implies that C is not isomorphic to its degree 2 Jacobian. And then which implies also that they are not stably birational because they are a genus 1 curve. And therefore, after you multiply by P1, so namely the birational class of the exceptional divisors of phi, also not birational to each other. And finally, we compose Q with the standard rationality construction. So namely, you project, you embed Q inside P4 and then project this Q from the point on Q. So that standard rationality construction has a vanishing motivic invariant. So this is the example for P3. Okay, so so now I will start talking about what I want to talk from the title, so the universal motivic invariant. So the question, or the goal is to, for us, is to understand. Okay, so now from the motivic invariant and non-vanishing theorem, we see that a priori, birational automorphism groups are not generated by regularizable elements. Now the question is, how can we further understand the difference motivically? So between B of X and so the normal subgroup reg of X generated by regularizable elements. Motivically. So let me provide you an answer. But first, I need to define another target of invariance, which we call Grothendieck group of pairs. Again, so we fix a base field K, and we consider the group. So abelian group denoted by K0 pair defined as follows. So as an abelian group, just as in the case of Grothendieck group of variety, we define it by generators and relations. So here, generators are pairs. So what are pairs? Pairs are open embeddings of non-empty varieties. So, and if the context is clear, then we also use the notation X comma U. So generated one for each open embedding. In relations, so there's a trivial one we need to put is when the open embedding is an isomorphism, then it goes to 0. And secondly, if you have a composition of open embeddings, then we have additivity. So namely, if you have V inside U inside X, then we have this chain rule. So XU is equal to XV is equal to XU plus UV. So that's it. So these are the relations we consider. let me draw some remark. So first of all, one way to formulate Grothendieck theorem is the following. If we consider a pair x, u, it is 0 in K0 of pairs. If and only if u is so isomorphic to x. So whenever you have an isomorphism, then for any open embeddings from u into x, it is 0 in K0 of pair. And the following further remarks we will not use, but which maybe is also of interest. First of all, so K0 of pair is a module over the Grothendieck ring of varieties. Yeah, so the multiplication is you take an element in or a generator in the Grothendieck ring of varieties and a generator in K0 of pairs. Then the multiplication is simply defined by this. And another remark is that K0 of pair is not only a group, but we can also define product and also, for instance, symmetric power. Yeah, in a similar way, we define symmetric power for elements in the Grothendieck ring of varieties. Okay, but we will not use the remarks, remark 2 and 3. Yeah, so let me just define what we call universal motivic invariant and then write an exact sequence which provide an answer to that question before finishing the talk. So universal motivic invariant. Okay, so given a birational map, F, and again, we choose a factorization by open embeddings. And then we define gamma F just as the difference x prime u prime minus x u. And this we regard it as an element in the K0 of pairs. And as an exercise of, actually the proof is the same as, the proof of the same properties for her C tilde. So exercise gamma is well defined. And the additive. Then the composition of the invariant is, the sum of the invariant is equal to the invariant of the composition. Now, so already this map, gamma, specializes to the motivic invariant C and also the invariant C tilde in the proof. And also, similarly, since by the additivity, if we look at the motivic environment of birational automorphisms, then this factorizes through the quotient here x modulo the subgroup generated by regularizable, a normal subgroup generated by regularizable element, and then take abelianization, because the target is abelian. So let me write down the following key proposition on the important property of this gamma and K0 appear. So proposition, we have an exact sequence. So we look at sum of all the birational automorphism groups over all varieties over K. And then we can apply the universal motivic invariant gamma, which arrive to K0 pair. And then we can further continue mapping K0 pair to the free abelian group generated by varieties. So this is just, you take xu and then send it to x minus u. And if you continue further, go to free abelian group generated by birational types, just send in x to the birational types of x. And this is clearly surjective. And this sequence is exact. And furthermore, if we restrict gamma to just one, the birational automorphism group of one variety, then what we have is that this universal motivic invariant is already injective. The moreover is split injective. So this justifies why we call a gamma a universal motivic invariant, because all the similar invariant with abelian group as the target factorizes through gamma. If this invariant takes regularizable elements to 0. So let me finish my talk here. Thank you very much.